In this tutorial, we will show the capabilities ETABS offers for the design of reinforced concrete slabs. Our design will be done for a typical floor slab in the concrete building shown, and although this design will be for gravity loads only, ETABS can perform analysis and design for lateral loads if needed. The building we are modeling is a residential structure, 8 stories tall, with bays varying in width from 18 feet to 20 feet. The structural system consists of concrete beams and columns on the perimeter, concrete walls in the interior that form the elevator core, concrete columns throughout the interior supporting gravity loads, and 8-inch thick concrete slabs for the floors. The units we will use will be U.S. customary, as shown here. In this tutorial, we are going to focus on the design of the typical residential floors, Story 7 and below. Story 8, which is the roof and has different loading, will not be included in the current design. Since we will not be designing the roof, we can remove Story 8 from our 3D view. We can verify our slab property by going to the Model Explorer and right-clicking on Slab 1. Note that the slab material is 4,000 psi concrete and that the thickness is indeed set to 8 inches. In a similar manner, we can also review our rebar material, and we will use A615 grade 6D reinforcing. We now move on to the load patterns. If we right-click on the dead load pattern, we see that currently 2 load patterns are defined, a dead load with a self-weight multiplier of 1 and a live load with no self-weight multiplier. To these 2, we will add a third, S-dead, to account for superimposed dead loads such as mechanical systems and non-structural walls. Next, we will assign the floor loads. We switch our selection option to similar stories so that when we assign loads to the 7th floor, the same loads will be applied to all of the floors below. We click on the 7th floor in the plan view and note that 7 shells are selected for the 7 floors. And go to the Assign Shell Loads Uniform command. The dead pattern will be just for self-weight, so we switch to the live pattern and assign a load of 50 pounds per square foot. It will be in the gravity direction. After clicking Apply, and with the form still open, we will click the previous selection button. Back on the form, we switch to the S-dead pattern, and this time assign a load of 20 pounds per square foot. We can now close this form. As a general rule, it is a good idea to include P-delta effects in our analysis, so we will specify that now. We are going to use an iterative method based on a combination of our gravity loads. With all of our loads now assigned, we will do a quick review of our load cases. Note that P delta is included in the load case analysis. Next, we will add the items needed in the model for concrete slab design. We will change to a plan view only and move the design menu buttons for easier access. ETABS can perform slab design using either the traditional design strips, where forces are integrated across a width to determine the reinforcing, or FEM, where the required reinforcing area is calculated on an element-by-element basis. We will show both. To add the design strips, we may draw them like other line type objects. Including specifying values using a properties of object box and the ability to right-click on the strip, which brings up the strip object information form. However, in this tutorial, we are going to use the automated scheme ETABS provides for design strip layout that can be found under the Edit menu. We will specify the layout for our top floor, floor 7, and the strips will be added along the grid lines. Make sure to check the Include Middle Strips option. If you were doing a post-tension slab, you would probably leave this option unchecked. The first strips that we will add will be added in the X direction for layer A. Typically, there are 2 principal layer directions. We will let the program automatically determine the strip widths. Although the strips extend beyond the slab, they will be ignored by the program when integrating the forces and determining the reinforcing. Now we will add the design strips in the Y direction, which will be for layer B. Again, information about a design strip may be obtained by right-clicking. And on the Geometry tab, we can review the start and ending widths that the program has calculated using the Auto Width option. We can also adjust how the strips are displayed using the Set Display Options command. Maybe we want to show only strip A and the strip width. Remember that we added the design strips to story 7 only. If we skip down a level, note that no design strips are shown on story 6. We can easily add the same design strips to all of the similar floors by using the Select by Object Type command. Highlighting both layer A and B, selecting, and then going to the Replicate command. We will replicate at story 6 down to story 1. Now if we skip down through the levels, note that design strips have been added. Now we may start the analysis. We will shut off the modal analysis case as we are not doing any dynamic analysis. With the analysis complete, we will review the settings for our concrete slab design. We start by viewing our design preferences. For this design, we are going to use the ACI 318-14 code. On the Cover tab, note the clear cover, and for this slab we are going to switch the preferred bar size to number 5s. This is the bar size the program will use when reporting reinforcing requirements. Note it changes to red to indicate the value has been altered. Also note that layer B will be the inner layer of reinforcing. Switching to the undeformed shape and moving to floor 7, if we select a design strip, and then go to the Design Overwrites command, we can see the particulars for this selected strip. In this case, it is an A layer strip on the column line, and the A615 grade 60 rebar previously reviewed will be used. We could also overwrite the cover to use, but we'll leave it as specified in the preferences. We could also reduce the live load used in design if so desired. If we take a look at the design combinations, we see that the form is currently blank. This is because the program will automatically generate the combinations when the design is run. We will check this again after the design is complete. When performing concrete slab design in ETABS, the user must explicitly select which stories should be designed. In this case, we will design only story 7, as the other floors are similar. This can provide not only computational efficiency on tall buildings, but can significantly reduce output, as slab design can generate very large amounts of data. We are now ready to start the design. What is displayed is the area of reinforcing required on a per unit width basis, top and bottom, in the A layer design strips. Note the values change as you scroll along. Also note that the extent of the top and bottom bars is indicated with the blue lines. We can change the display by going to the Display Flexural Design command. Here we are asking for the results using strips, and since we have no post-tensioning, enveloping in the display type option simply means strength design. And it is the flexural reinforcing needed to satisfy strength design that we are displaying. However, if we wanted to additionally impose code minimums, we could do so by checking the Impose Minimum Reinforcing checkbox. Switching to layer B, and then checking the top rebar, we will ask for the total rebar to be shown just for the bottom rebar. Switching back to layer A, we will ask for reinforcing to be shown in terms of number 5 bars. We can switch off the enveloping and show only the rebar required above typical if desired. If we right-click on a design strip, design details for the strip are displayed. Although all the slab reinforcing shown so far has used the design strips, reinforcing may also be calculated directly from the finite element forces. We do this by selecting finite element base as the design basis. Here, reinforcing direction refers to the local axes of the slab object. We will select bottom rebar in the one direction, which for our model is the same as the x-axis. Running the cursor over the model displays the reinforcing area per unit width. We can also show reinforcing above a specified value. The FEM design basis provides the user with a powerful visual indication of how the reinforcing should be distributed. ETABS also automates the checking of punching shear. Once design has been run, a punching check is available by clicking the Display Punching Check command. Punching check ratios are displayed on the plan. Again, a right-click on a punching check location will display design details for that location. Returning to the concrete slab design menu once more, we will now revisit the design combinations form. Note that design combinations have now been created. We can quickly review the combinations generated by the program if so desired. We can also generate a report of our slab design results. We will ask for design results for just load combinations, and we'll deselect all items other than that for the concrete slab design results. As stated previously, concrete slab design generates substantial data output. As a last step, we will take a look at a summary table for our concrete slab design. Note that it says flexure and shear. Although up to this point, we have been primarily concerned with flexural reinforcing in the slab, as shown here in this table. ETABS also performs shear design for slabs, and the shear design results and reinforcing are available here. This concludes this tutorial on reinforced concrete slab design in ETABS.